The Great Barrier Reef stretches across roughly 2,300 kilometers of ocean off the coast of northeastern Australia, and it is the only living structure on this planet large enough to be seen from orbit. No engineer designed it, no single organism built it, and yet it has grown into the largest structure ever assembled by living things on Earth. Since 1998, it has been struck by mass bleaching on at least 7 separate occasions, and 4 of those events have landed since 2016 alone. What follows is a count of what researchers have actually documented, the mechanism, the damage, and the handful of sections that, against expectation, appear to be holding on. One of those findings, saved for the end, has left marine biologists genuinely divided about what recovery even means. Here's what we actually know about the scale. First, the reef is not one organism, but an interconnected system of more than 900 islands and reefs, built from the skeletons of hundreds of species of hard coral, layered over thousands of years. There is a widely repeated claim that the Great Wall of China is visible from space with the naked eye. Astronauts and multiple space agencies have said this is false. The Great Barrier Reef, by contrast, genuinely is visible from low Earth orbit, its pale blue-green mass unmistakable against the darker water around it. That contrast, one famous claim that collapses under scrutiny, and one lesser-known fact that holds up, is a useful place to start, because precision is going to matter for everything that follows. Officially, the explanation for coral bleaching is simple. The problem is that bleaching gets used loosely in casual conversation, and that loose usage hides the actual biology. Coral polyps host microscopic algae called Zooxanthellae inside their tissue, in a relationship where the algae photosynthesize and pass most of that energy back to the coral. When water temperatures rise even slightly above the coral's tolerance for a sustained period, the coral expels these algae as a stress response. What's left behind is the coral's white calcium carbonate skeleton, showing through nearly transparent tissue. That's the bleaching itself, not death. That distinction is where most reef coverage quietly falls apart. Bleached coral is alive. If water temperatures drop back within roughly a few weeks, the coral can reabsorb or regrow its algae population and recover close to its original state. If the heat stress continues for longer, the coral starves, becomes vulnerable to disease, and eventually dies. But the bleaching event and the coral death are two different sequential things, documented separately in survey data. Conflating them is exactly how a genuinely alarming statistic gets inflated into a false one. Or, just as often, how a real die-off gets waved away as just bleaching. It'll bounce back. That's worth sitting with for a moment, because it cuts against the instinct to treat every reef headline as either catastrophe or overreaction. The honest picture requires holding both possibilities at once, and researchers who study the reef professionally tend to get frustrated with coverage that picks one side and ignores the other. Whether media coverage of the reef has done more harm through exaggeration or through complacency is genuinely arguable, and it's worth arguing about, because both failure modes have shaped public understanding of what's actually happening out there. The first mass bleaching event on record affecting the reef broadly was documented in 1998, followed by another in 2002. Both were serious, but what happened starting in 2016 changed the pattern entirely. Aerial and underwater surveys conducted by researchers, including teams from the ARC Center of Excellence for Coral Reef Studies, found that the 2016 event was the most severe bleaching the reef had experienced up to that point, concentrated heavily in the reef's northern third. Surveys estimated that a large share of shallow water coral in that northern section died within months, not bleached, but dead, confirmed by repeat dives at the same sites before and after the heat event. Here's the detail that doesn't fit the usual disaster narrative of a single bad year followed by recovery. The reef did not get a recovery year. In 2017, a second mass bleaching event hit again, this time concentrated further south, overlapping with reef sections that hadn't yet recovered from the previous year. Researchers had never documented back-to-back mass bleaching events on the reef before that pairing, and the compounding effect, corals stressed twice in successive summers with no full recovery window between them, was itself the alarming part, more than either event taken alone. What makes this trackable in such detail is a monitoring effort that predates the crisis by decades. The Australian Institute of Marine Science has run a long-term reef monitoring program since the mid-1980s, combining fixed-site diving surveys with aerial reconnaissance flights that let researchers assess bleaching extent across enormous stretches of reef in a single season. That's how the 2016 and 2017 events could be mapped reef by reef, rather than estimated from a handful of sites. And it's the same infrastructure that caught what came next. A third mass bleaching event was confirmed in 2020, and this one broke a pattern researchers had been counting on. Previous mass bleaching events had all coincided with El Niño conditions, when Pacific Ocean warming pushes regional sea temperatures up. The 2020 event happened without El Niño present. That single fact mattered more than its severity ranking, because it suggested that background ocean warming alone was now sufficient to trigger reef-wide bleaching, without needing an additional climate cycle to push temperatures over the edge. If topics like this hold your attention, the kind of place where the documented record keeps producing details stranger than the popular version of the story, this is roughly the point in a Beyond the Maps video where it's worth hitting subscribe. Because what's coming next is the detail that actually divides researchers, not just the damage report. 2022 brought a fourth mass bleaching event, and it broke an even more specific expectation. This one occurred during a La Niña phase, a Pacific climate pattern that typically brings cooler, wetter conditions to the Australian coast, and had previously been associated with reef recovery periods, not bleaching. Surveys confirmed bleaching across large sections of the reef regardless. Researchers were forced to conclude that the reef's climate-linked safety margin, the cooler years it used to lean on for partial recovery, could no longer be relied on as a buffer. Then came 2024, documented as the most widespread bleaching event on record for the reef, affecting reef sections from the far north down through the central and southern regions in the same season, based on aerial surveys covering more than 1,000 individual reefs. For the first time, a single event touched nearly the entire length of the system rather than concentrating in one section. That should have settled the question of the reef's trajectory. It didn't, because the same surveys that documented the extent of the 2024 bleaching also documented something researchers were not fully prepared to explain. Here's what the data doesn't explain cleanly. Within reef sections hit hard in 2016 and again in 2024, survey teams identified individual coral colonies, sitting meters from neighbors that bleached and died, that showed measurably higher heat tolerance, and survived both events largely intact. Genetic sampling has linked some of this to specific Zooxanthellae strains that handle heat stress better than others, and to coral populations with prior exposure to warmer water, in places like reef flats that naturally run hotter. But why certain individual colonies within the same species, in the same water, under the same thermal stress, survive while their genetic near relatives die has not been fully resolved. And it's one of the more consequential open questions in reef science right now, since it may determine which parts of the reef have any long-term future at all. This is where most explanations quietly stop, but the resilience data adds a second layer that complicates it further. Some of the fastest recovering coral species after a bleaching event are also, ironically, the most vulnerable to the next one. Fast-growing branching corals in the genus Acropora can repopulate a damaged reef section within a handful of years, which looks like strong recovery in survey photographs. But those same fast-growing corals tend to have lower heat tolerance than slower-growing, denser coral species, meaning the sections that look recovered fastest may be rebuilding themselves out of the coral types most likely to bleach again in the next hot summer. Whether that counts as genuine recovery or a fragile rebound dressed up as one is a distinction survey photographs alone can't settle. No one disputes that the reef has lost a substantial share of its coral cover since 2016, with AIMS monitoring data showing significant declines in hard coral cover across northern and central sections through the repeated bleaching years. It's the second part that causes the argument among researchers, whether the documented pockets of unexpected resilience represent the beginning of natural adaptation happening in real time, or whether they're simply the surviving remnant of a system that is still, on net, losing ground faster than it can recover it. Long-term projections from reef scientists diverge sharply on this point. And that divergence itself is worth noting, because it means the honest answer, as of now, is that no one knows which trajectory is winning. So return to that first image. A structure of ocean visible from low orbit, stretching 2,300 kilometers along a coastline, built without a single architect. What's proven is extensive and well documented. 4 mass bleaching events since 2016, a clear biological mechanism behind each one, confirmed coral death in specific surveyed sections, and a monitoring record detailed enough to track individual reefs year over year. What remains genuinely unresolved is smaller in scope but larger in consequence. Why specific coral colonies survive heat stress that kills their neighbors, and whether the reef's demonstrated capacity for partial recovery can keep pace with a rate of ocean warming that shows no sign of slowing to match it. That gap between a system large enough to be seen from space and a recovery mechanism that still depends on individual colonies researchers can't fully explain is not unique to this one reef. It's the same gap facing coral systems worldwide, just documented here in more detail than almost anywhere else on Earth, because more scientists have spent more years watching this particular stretch of water than any other. Whether the coral colonies that survived 2016 and 2024 will still be there the next time a marine heat wave moves through the Coral Sea is a question the data cannot yet answer. Only the next set of surveys will.